Now, the last thing that we did was the following. We had two random variables, xi1 and xi2. And we say, okay, let's compute the variance of xi1 plus xi2. So the variance of the sum of two random variables. Okay, and we obtained that. What is the result that we obtained for that? Plus something else, right? And that something else was the following. So 2 times the expected value of xi minus the expected value of xi, and sorry, xi1, expected value of xi1, and xi2 minus the expected value of xi2. Okay? So the first thing is the following. So the first thing that we have to do is to call this, so this expected value right here, this is now a new number, a new characteristic, but now not from only one random variable, because we had that. So for the expected value, we had the expected value of xi, so the expected value of only one random variable. We had the variance of xi, but now we have the some characteristic of two random variables, right? Xi1 and xi2. And this is what we call the covariance of xi1 and xi2, okay? So this is the covariance between two random variables, xi1 and xi2. And the covariance is going to give us the following information: how dependent xi is from xi2, right? So how dependent are xi1 and xi2 from each other? This is the information that we will obtain from here. So if the covariance is about 0, then we will understand that they are highly independent, okay? But if the covariance is a huge number, then the dependency is really big, okay? Something like that. It's not clear how dependent they are depending on the number, right? But we'll see it in 1 second. So look, so the definition is the following. So definition, so we call this, right, the expected value of xi1 minus expected value of xi1 times xi2 minus expected value of xi2, the covariance between random variables xi1 and xi2. Okay, so look, if xi1 tends to be higher than the expected value, then this number is positive, right? If xi1 tends to be higher than the expected value, then this is positive. And the same for xi2. So if xi2 tends to be higher than the expected value of xi2, then this number is positive. So we obtain that if both xi1 and xi2 tend to be higher than their expected values, then this number is going to be greater than 0. Yes? In the same way, if xi1 tends to be lower than the expected value of xi1, then this is negative. And this number will be negative as well, right? So we can see that then the product is going to be positive. If at the same time xi1 and xi2 are higher than their expected values, then this product is going to be greater than 0, right? If at the same time xi1 and xi2 are below their expected values, then this product is going to be also greater than 0. So we can see that if xi1 and xi2, they both increase somehow, yeah, then the covariance is going to be greater than 0. If they both decrease, then the covariance is going to be greater than 0. Okay, so look. This is how to say, just a sec. This is xi1 here, this is xi2. So if xi1 increases and xi2 increases, so if we have something like this, so in this case, we have that xi1 increases and xi2 also increases. Yes? In this case, we obtain that the covariance is going to be positive. And if xi1 decreases and xi2 decreases, so this also, then the covariance is also greater than 0. On the other hand, If psi1 increases, but psi2 decreases, so we can see that this is greater than 0 because it increases, so it's higher than the expected value. But this one, this psi2 will be below the expected value, so this will be negative. So the product will be negative. So in this case, we will obtain that the covariance will be less than 0. Okay? So if both increases, right? So if psi1 and psi2 they increase, then the covariance is positive. If psi1 and psi2 decrease, then the covariance is positive. But if one increases and the other decreases, then we can see that the covariance will be negative. Okay. Now, what the other case is? What if we have something like this? Just this straight line here. Then we have that psi1 increases, and what happens with psi2? It's constant, right? So what conclusion can we make? Psi1 is changing, is increasing, and psi2 just doesn't change. So it means somehow that psi2 doesn't depend on psi1, right? Because it doesn't matter how psi1 is changing, psi2 keeps the same. So somehow they should be independent somehow, right? So psi2, so here we have some constant. So we can see that psi2 doesn't depend on psi1 somehow, right? So now let's formalize all of that right here. So this is the definition. And now we have the properties here. So the first property is the formula that we use to compute the covariance. So we'll have that the covariance between psi1 and psi2, we can compute it as the expected value of psi1 multiplied by psi2 minus the expected value of psi1 multiplied by the expected value of psi2. Right. Yeah. So this is the first property. Is that so formally this is the definition that we have for the covariance, but the formula that we are going to use to compute the covariance is this one. So the expected value of the product minus the expected value of psi multiplied by the expected value of psi2. Now, we already know that if psi1 and psi2 are independent, then the product is equal to the product of their expected values. So this will be 0. So we already know that, so this is property number 2, that if psi1 and psi2 are independent, then the covariance between psi1 and psi2 will be equal to 0. Okay? So this is already, we already know this. We already know this. We already know that, well, we already proved this part, right? So we already know this. If psi1 and psi2 are independent, then the covariance is going to be equal to 0. But if the covariance is equal to 0, it doesn't mean that they are independent, okay? We haven't had any example for that. We will have today for sure, okay? Now, property number 3, linearity of the covariance. So let, for every a and b from the real numbers, right, and 2 random variables, psi1 and psi2, we'll have that the covariance of a psi1 plus b psi2 and eta, okay, this will be equal to a times the covariance between psi1 and eta plus b, the covariance psi2 and eta. Linearity of the covariance, okay? So this is the second property. I don't know, what other property do we have? Yes, symmetry. Property number 4 is that the covariance between psi and eta is equal to the covariance between eta and psi. Okay, this is the same. And property number 5. So what do you think is the covariance between psi and psi? Is the variance, right? Good. So these are the properties that we need by now. So let's prove number 1. Proof of 1. Well, we have that the covariance xi and eta, it's given by the expected value of xi minus the expected value of xi times, okay, let me use xi and eta, it's better xi and eta. Xi1 and xi2 is a little bit confusing, right? We don't see the indexes, very good. So xi and eta. So here we have eta minus the expected value of eta. So, well, all that we have to do is we have to multiply here xi by eta. So we have expected value of xi eta. Then we have, well, xi minus xi and the expected value of eta. Then we have minus expected value of xi and eta, and plus expected value of xi multiplied by the expected value of eta. Okay. So what is this? This will be equal to the expected value of xi times eta. And here we have minus. We'll have minus 2 times the expected value of xi. Wait, so here we had not like this. It's better like this already, so that we don't get confused, right? So here we had the expected value of xi multiplied by eta, not the expected value of xi eta. Then we have minus 2 times the expected value of xi times the expected value of eta plus the expected value of xi multiplied by the expected value of eta. So we obtain that this is equal to, well, what we are looking for, expected value of xi times eta minus the expected value of xi times expected value of eta. That's it. Right? So this is the formula that we need to use to compute the covariance. Okay? Now, what is important to notice from here? It's important to notice that the covariance is any real number. So the covariance can be 0, the covariance can be 1, or the covariance can be 1 billion. Okay? Any number here. So that's why it's not very clear. How can we define what kind of independence we have? Because we can have any number. So how can we compare that the covariance is equal to 5 or to 5 million? Right? So we'll need to fix that a bit later. Okay. By now we just have the formula to compute it. So that's the covariance. Now, so this property, the second property, we already know this. We already know the property with the proof. Now let's prove this one. Okay, number 3. Well, so we have the covariance of xi1 plus covariance of xi1 plus bxi2 in eta. Well, we just have to write the formula. Let's use this one. I think this one is better to use. And let's compute it. So we have, this is equal to the expected value of this multiplied by this. Right? So xi1 plus bxi2 multiplied by eta, right? The expected value of the product minus the expected value of this multiplied by the expected value of this. Yes, expected value of xi1 plus bxi2 multiplied by the expected value of it. Yes? So all that I'm doing is that instead, so here I had that the covariance of xi and eta is equal to this. I'm replacing this formula whenever xi is equal to xi1 plus bxi2 and eta is just eta. I keep eta, right? So that's all that I'm doing. So this is equal to this. Now next I have to solve this and to get, well, this right here. Okay? So we can see that we need the common factor A and the common factor B. So let's do that. So here this is equal, so look, A is right here, yes? This will be what? This will be A times the expected value of xi1 and this multiplied by eta. Wait, no, here it's like this. This is close, yes. So xi1 eta, yes? So this comes from here. This comes from here. And from here we have minus A, the expected value of xi1 multiplied by the expected value of eta. So I can write here A, here minus expected value of psi1 multiplied by the expected value of eta. Yes. And now I do the same for B. Plus B, I open brackets, and I will have the expected value of psi2 times eta minus B expected value of psi2 times the expected value of eta. And what is this? This is the covariance between psi1 and eta. Yeah, so this is equal to A times the covariance between psi1 and eta plus B times the covariance between psi2 and eta. That's it, we prove it. Yeah. So this is very simple to do. I mean, the difficult thing here are not the proofs and all of that, but how to apply these to problems. That's where the things get interesting. Right now, it's just linearity everywhere, right? Mm-hmm.
A times expected value of psi1 and n.
Right here,
Yes.
psi1. So the expected value of psi1 and eta, the product, everything is inside. Yes. And here minus this. Yeah? Okay, good. All right. So what else do we have? So we already did this one. Now number 4 is clear from the formula. If you change psi by eta, you obtain exactly the same formula. So this is done. Yes.
I just wanted to confirm, these formulas and properties, these are for discrete random variables? Or for
No, this is for any random variables.
okay.
Yeah. So everything that we've been doing for the properties of expected value and variance and all that, this works for all random variables. The difference is that we prove some properties of the expected value only for the discrete case. We prove it for the discrete case, but they also work, not the proof, but the statement itself. The property works for any random variables, okay? Just the difference of the proof is that instead of the sum, we will have an integral. Okay, so property number 4 is clear, and property number 5 is also clear. If you replace here psi by eta, you obtain the expected value of psi squared minus the expected value of psi, everything is square. So this is the definition of the variance that we have right here. Okay? Now that we know these properties, we can find finally what is, so this is, let me call this a claim. I need to find the variance of the sum of n random variables. So let's find that, and then I will replace it, and we'll have the claim, right? So now, what is the variance of the sum of n random variables? So we already know that the variance of the sum of two random variables will be the variance of psi1 plus the variance of psi2, right here, plus 2 times the covariance between them, right? So this works whenever we have only 2 random variables. Now we don't have 2 random variables, we have n random variables. Now, what do we have to do? So look, in order to prove this, well, we could say maybe by induction or something like that, right? But there's no need because we know that the variance of a random variable, so this is one random variable, okay? So we have one random variable here, the sum of random variables. But we know that the variance of a random variable is the covariance of this random variable with itself, yes? So the variance of this sum is equal to the covariance of the sum with itself. So this is the covariance of psi1 plus psi-n, and here we have psi1 plus psi-n. Yes, we know this. And let me continue here so that everyone can see. So let's find this. We have by linearity, we already proved linearity for this. So we know that this is going to be what? So first we will have covariance. Look, we'll have covariance of psi1 and psi1 plus the covariance of psi2 and psi2, psi3 and psi3, and so on. So this is the first part. So we'll have here, let me write it, covariance psi1, psi1 plus covariance xi2, xi2, up to covariance of xi n, right? So this is the first thing, the first part that we obtain when we have exactly the same index right here. So we have covariance of xi, right? So the index is the same. And the other case is when we have different indexes. So we have here the covariance of xi1, xi2, xi1, xi3, xi1, xi4, and so on. So we can see that we will have, look, the covariance of xi1, xi2, and then we will have the covariance of xi2, xi1. So we have 2 times. So let me write it like this. So we have plus covariance of xi1, xi2, plus covariance of xi1, xi3, up to covariance of xi1, xin. And right here we will have covariance of xi2, xi1. Yes, and so on. So, but we already know that the covariance is symmetric. So the covariance of xi1, xi2 is exactly the same of the covariance of xi2, xi1. So we can write this in the following way. So what is the variance of xi1, xi1? It's the variance of xi1, right? So this is just the sum from 1 to n of the variance of xi. Yes. So this is this part right here. And this will have 2 times, because we can see that we have covariance of xi1, xi2, and xi2, xi1, which is the same. So this is the same of having 2 times the covariance of xi1, xi2. So this will be 2 times the sum over all. So here we have all different indexes, I and j. So I less than j, like this. And covariance between psi I and psi j. That's it. So this is the general formula. This is the claim. So here you can replace this by that. And that's it. So this is how we compute the variance of the sum. Okay?